Hi, welcome back. So last time we started chapter one, we talked about simple combinations for resistors. Today, we're going to look at some more complicated combinations for the resistors, and then um, another way that we can solve for the problem if the circuit becomes so complicated. And then we'll look at the meters, voltmeters and ammeters, and then also on ohm meters as well. But let's jump in here. All right, so a quick review. Last time, if we have resistors in just series or in parallel, then these two scenarios are the opposite to the capacitors in series or in parallel. So if the resistors are in series, the combination can be represented by an equivalent resistor, which then equivalent resistance for the resistors in series, which is just the resistance of each one add up. And then if they are in parallel to each other, then this is similar to capacitors in series, which you will do inverse of each resistor's resistance, add up, and then do the inverse again at the end to find the equivalent resistance of the combination. Okay. All right. So sometimes the circuits becomes a little bit more complicated. So then um, in this case, let's take a look on this here. So in some part of circuit, you have the resistors in parallel, and then here you have them also in parallel, but these three and these two, combination of these two and the combination of these three, then they are actually in series to each other, okay? And then all this together will be in parallel with this guy. And then at the end, this one will be in series for the rest on this side here. So the circuit becomes so complicated. So then what do we do about this? Okay. So this will be similar again to the capacitors combinations. So you'll look at the part of this circuit that's only having just capacitors either in series or in parallel. Okay. And then put a equivalent resistor for that part of the circuit, and then you will go on from that point. Okay, so each time you look at the just the resistors or the equivalent resistors that are just purely in series or in parallel, and then replace that part of the circuit by an equivalent resistor, and then move on, okay, to the next step. So we'll treat these two are in parallel, just purely in parallel, and then these three are just in parallel. So we'll replace these two with the equivalent capacitor of R prime sub P, and then this guy will be the R sub P. Okay, the three combination will be replaced by just one single R sub P there. So then now this circuit becomes this one with this guy representing these two, this guy representing these three. Then these two now just in parallel to in series to each other. So these two will be replaced by a R sub S. Okay, so then this part becomes just one R sub S here. Now this R sub S and then this R1, they are actually in parallel to each other now, and just purely in parallel. So then these two can be replaced by a RP double prime, the second combination in parallel, and then replaced by that P double prime. So then becomes this circuit. Okay, so then these two now at the end just purely in series, and then can be represented by this guy. Okay, so you just do step by step in that case. Okay, all right. So let's take a look at this example here. It says, consider the circuit showing here, find A, the equivalent resistance of the whole circuit, okay, and then B, find the current through each of the resistors, okay? So we'll take a look at the two questions one by one. So here, so first, we'll analyze the circuit here. So this one is in series with this part, okay? Now inside this part, inside this part over here, so maybe just look at one by one inside this part, okay? So if we look at inside this part, you can actually break it down as like this, at this point B, and then there's this 6.2, and then there's this 12, and then there's this 7.5, zigzag there. Okay, so this will be where the potential will be applied. So 6.2, 12, and then 7.5. So the 6.2 and 12 is in series. So those two are in series. So combination of resistor in series, you just add them up. Okay, so that's 18.2. That can be replaced by 18.2. So now this part becomes just 7.5 here, right? And then now this, the 2 replaced by 18.2. So this is 18.2. Okay. So the 7.5 and 18.2, they are actually in parallel to each other. So then this whole thing can be replaced by uh, equivalent capacitors of those two in parallel. You can calculate in parallel should be you do inverse of the two resistors plus each other, okay? And then inverse for the equivalent, okay? So if you do that, it will give you, take a look on what we have here. So 5.31 actually. So 5.31 ohms on this. So this whole thing is 5.31 ohms. So then your resistor now becomes, or your circuit here, I can move it over here. So this guy, battery, and then this whole thing is replaced by a resistor of just 5.31, 5.31, and then this one here, the 11, okay? So now these two are in series to each other, so you just add them up, okay? So the equivalent at the end, Req at the end should be just the 11 plus the 5.31. So that will be 16.3 ohms, okay? For part A, your equivalent um, resistance for the whole thing, whole circuit. Okay, so for part A. Part B is asking you what then would be the current through each of resistors. So current through this guy, through this one, through this one, through this one. Okay. So for the current, we can imagine that it will flow out of the positive terminal. Okay. And then going this way, at point B here, it will split into two, one going this way, the other one goes in that way. Okay. And then those two will merge over here, down here, and then that total will go through the 11 ohms. So in this case, for the current, we can find out the current for the whole circuit. Okay, so for the whole circuit, in part B here, I is equal to just the voltage from the battery divided by the Req of the whole thing. Okay, so that's 15 volts divided by 16.3 ohms. So that will give you 0.92 amps of the current. And this current is for the whole circuit. So then it's this current going out of the battery here, split into two, and then merge back, and then through the 11 ohms resistor. So this guy is also the I for the 11 ohms. Okay, so you can write like that. Let me just 11 ohms. Okay, so that guy for that. So we have found one current for the 11 ohms. Now, the 11 ohms, the current through the 11 ohms will split into two. Okay, so this is 11 ohms, and then it will split into this one, and then as well as that one. Okay, so these two are in parallel. So then to find the current through this guy, we can find the voltage across this one, right? And then voltage divided by this guy will be that. And then this current, then you can do the same thing. Voltage divided by the combination of these two will be the current there. Or you can do the current through the total current minus that guy. Okay, so either way, these two are in parallel. So these two, or this whole combination is replaced by this single one. So then we can just take a look at what will be the current through this single one. Current through the 11 is known. So through this guy, we have found it 0.92. Okay. Amps. And then, so in that case, and then current through this equivalent should be also that. Okay, so we can find that voltage across this equivalent, V on that, on the 5.31, 0.31 would be, that's ohms, will be the I, according to Ohm's law, will be the I times the resistance, right? So it's the 0.92 amps times the 5.31 ohms, and that will be 4.89 volts. Okay, so that's the voltage across this equivalent resistor, which means it's the voltage across this whole combination, because the whole combination is replaced by the single one. Okay, so then the voltage between this point and that point is the 4.89. So then I through the 7.5 ohms, you can calculate that. I for the 7.5 ohms sub 7.5 ohms is then the 4.89 volts divided by 7.5 ohms. So that will be 0.65 amps on that one. Okay. The same thing you can do the voltage across these two. Okay. So they are in series, so they will share the same current, or looking for the current across these two. Okay, so we're looking for current there. So I on the 6.2 is the same as I on the 18 ohms. Okay, and that should be equal to 4.89 volts divided by the combination of the two, these two together is the 18.2 ohms. So that will give you 0.27 amps. Okay, so we can find that. So you can break down the circuit and then do part by part for the whole thing. Okay. All right. So let's go back to the PowerPoint. Okay. So if you just have one battery in the circuit, okay, so then for complex circuit, you can still break down just part by part, but sometimes there's more than one battery in the system. Okay, so let's take a look on a circuit like this. So there's this one battery here, there's this resistor, those resistors, and then there's another battery over here. So now these resistor and this one is not just simply in parallel with each other, because there's another element over here. Okay, so when you have more complicated circuit that cannot be broken down into series and in parallel pieces, then you will to use Kirchhoff's rules. Okay, so there are two rules here. One is called the junction rule. So, and then the other one is called the loop rule. The junction rule is basically the conservation of charge, and the loop rule is conservation of energy. Okay, so for the junction rule, we'll take a look at the junction rule first. Okay, so any junctions in the circuit, the current entering the junction must equal the current leaving it. So for example, here, if a current comes in, split into two, so then I1 should be equal to I2 plus I3, or I1 minus I2 minus I3 equal to 0. Okay, if you have two currents comes in, I1 plus I2 equals to them I3 plus I4 in that case. Okay, just in that case, but the currents goes in should be equal to the currents go out. Okay, the junction, which is pretty much the charges, right? Conservation of charges. So how many charges comes in should be equal to how many charges leaves out at the same time. The loop rule is then dealing with the conservation of energy, which energy is related to voltage. So basically, if you are starting from A and then going through a loop, coming back to A, you should get the same voltage. So that means change in voltage from A to A back to A should be equal to 0. Okay. And then energy, electric energy and potential, they are proportional, directly proportional to each other with the Q. So in that case, okay, so then it's also potential consistent, and that means energy also consistent in that case, okay. But here, if you go from point A through B through C, D, and back to A, so this is complete loop, okay. So then the potential across each element should add up to be 0. Okay, so potential across this guy plus the potential across this guy, it should equal to 0. For the wires, typically we'll ignore any resistance through the wires because they are conducting. Okay, so in that case, but we'll just look at the electrical elements in this circuit. When you are going through, when you are going through a battery, so the voltage changes is as this. So if you across the battery from the negative terminal to the positive terminal, your voltage increase. Okay, so in this case, you will say epsilon, whatever, 6 volts or 9 volts, 12 volts battery, whatever it is, will be plus of that epsilon. Okay, so plus 6, plus 9, plus 12. Okay, and then going through a resistor. So it depends on the current direction and then also the loop's direction. Okay, so if you are going in the same direction of the current, when the current and loop cross the resistor, then you have potential decrease. Okay, so potential decrease from this side to the other side. So then, for example, if I is equal to 1, if I equal to 10, then this change in potential will be minus 10. Okay, so this will be actually minus, okay, minus IR if current and loop are in the same direction. Now, if your loop goes against the direction of the current, so let's say if you are going from A, D, C, B, so then you will have increase because current and loop direction are against each other, okay? So then the voltage will be positive. And then from positive terminal to negative terminal, that will be negative, okay, of the current, of the voltage change. So these are the Kirchhoff's rules. All right, so you can use as many loops and as many junctions as you like to form independent equations, and then you can solve for several variables. Okay, so if you are looking for 3 variables, you will need 3 independent equations. Okay, a lot of times you'll use both junction and loop rules to achieve that. Okay, we'll take a look at a couple examples and then show you how to apply Kirchhoff's rules. Okay, so the first one will be a very simple one. It's only one loop, but now you have actually 2 batteries, okay, in it. So there's one loop here. So we can say, let's do maybe starting from point A, okay? So if we do point A, let's see. I'm going to just have to find my notes here. Yep, maybe not. Oh yeah, it's here. All right. So if I start from point A, Okay, let me switch over. All right, so if I start from my point A here, right, and then A, B, C, D, so my loop's direction is in this direction. Okay, so this is my loop's direction. This is clockwise. So there's no junctions here because it's only one single loop. So I can only apply a loop rule here. So I'm going in this direction, all right, and then in this case, I can see because this is positive, so current should be going out from here, and then also on this battery is going out from there. So looks like the current is going in that direction, okay? Also the same direction as my loop, okay? So this is direction of I, and then that's my loop, okay? So the same direction, the current and the loop, so that means my voltage should be negative, negative of I times the 15.1 ohms, okay? And then this is the first element I'm encountering. Now the second one here is the battery. I'm going from negative terminal to positive terminal. So my voltage should increase, okay? So I should have plus now, 15 volts on that. The third element is this guy. Current and loop are in the same direction. So then again, it's plus I times or minus instead of plus because it's the same direction of current and loop. So it'll be minus I times 8.5 ohms. Okay. Now the third element I'm encountering is this battery again. So this will be, I'm going from negative terminal to positive terminal. So again, it's plus, okay, 11.5. And the last one is this current and loop are in the same direction. So this will be again minus of I times 6.22. Okay. And now I'm coming back to my point A. So all this add up should be equal to 0 because you are going through a complete loop. Okay. So voltage should go to 0. Okay. So I can find my current because there's this guy, and this guy. Okay. And then voltages, there's two numbers there and there. Okay, so maybe I can put all the current to one side of equation. So I'll add those up. Okay, so this will be just the negative of 15.1 minus 18 minus 8.3, not 18, 8.3, and then minus 6.22 all together times I. And then I'll move the other two numbers to the other side of the equation, so they become minus of 15 minus 11.5. Okay, so my I then at the end should be everything is negative, so they will become positive. You can flip those signs. Okay, so then it will be 15 plus 11.5 on the top, divided by 15.1 plus 8.3 plus 6.22 at the bottom. Okay. So then I can find my current to be 0.889 amps. Okay? So the current through this circuit is 0.889 amps. All right, so this is one example. And then the simple one. Now let's take a look at the second example. Okay, so this one is the one that's shown up earlier. A little bit more complicated. Okay, so here it says find the current goes through each of the resistors showing here in the figure. Okay, so we can take a look at this guy over here, and then let's see. I'm trying to find my notes. Got a few pages here. I don't know which one. Is the right one? Okay. Anyway, it probably doesn't matter, but oh, I think I found it. Okay, here. So in here, there's one junction here. Okay, so we can see we are looking for current going through each element. So let's say if we have current going out of this left battery over here, okay, and then when it hits point A, it's going to split into two. So one current going through this guy, and then one current going through that guy. Okay. So at junction A, so let's call this guy as I of one, and then it splits into two. Let's call this one as I of two, and then this guy as I of three. Okay. So then my I of one should be equal to I of two plus I of three. Okay. So I have one equation now. These two currents, I of three, will come in this way. Okay. They will merge at this point, and then will become I of one here again. So there are two junctions here, A and this guy down here, but these two seems to be giving you the same equation because on the top here is I1 equal to I2 plus I3, and the bottom here is I2 plus I3 equal to I1. So they are identical. So it's just one equation, okay? So then on that, now we have used our junction rule. Now maybe look at the loop rule. So we can pick a loop here. So this guy here, let's say goes in that direction, and then this guy goes in this direction as well. Okay. So this is loop number one. This is loop number two. So according to my loop one, let's start from, let's say here. Okay. And then going through the whole loop. So starting from here, going through the whole loop and then coming back to the starting point. Okay. So the voltage changes across all these elements should be adding up to zero. Okay, so the first one, loop's direction in this direction goes from negative terminal to positive terminal. So then this should be positive. It should have a voltage increase. Okay, so we'll write down in 12 on that one. First one. The second element, this resistor, so I1 and direction of loop across this guy is the same direction. So we say minus 3.9 of I1. This one here, I2 and the current direction, again, that's the same. So it's minus 1.2, okay, of I2, okay. Now coming back here, this 9.8, current direction, loop's direction, the same. So this is also minus 9.8 of I1. And then going back to the starting point, so that should be zero, okay. So that's your loop one. Your loop two, we'll start at, let's say from point A and then through this resistor, through this guy, and then through this 1.2 ohm goes back to A, okay? So loop's direction, current direction the same. So it's starting with minus 6.7 I3. And then on the battery here, you are actually going from positive terminal to the negative terminal, so it'll be minus 9, okay? And then I3 here again. Now this loop's direction is against current I2's direction. Okay, so remember this is I2, this is loop 2's direction, they're against each other, so then that becomes plus 1.2 times I2. Okay, then it goes to zero. So now you have those three equations. There are three unknowns in the equations. Okay, so three independent equations will give you three unknowns. Okay, so that's algebra. But let's take a look on this together. So with three unknowns, you this is the way to solve three equations with three unknowns. Okay, so you'll use one common unknown and then write the other two unknowns in terms of that common unknown from two equations, and then now put these two expressions of the two unknowns to a third equation. Okay, so basically this is what we need to do. We need to take this equation because there are two unknowns in it. We'll write I1 in terms of I2, okay? And then we can look at this equation as well, because there's I2 and I3. There's the second equation has I1 and I2. The third equation has I2 and I3. So the common unknown amount between these two equations is I2, okay? So then this guy will give us I1 in terms of I2, okay? So we'll isolate I1. So there's I1 here, there's I1 here. So these two should add up, okay? So then this equation becomes 12 minus 1.2 I2 equals to, move these two to the other side, becomes negative, becomes positive, okay? 3.9 plus 9.8 times I1, okay? So then these two add up to be 13.7. So then I1 equals to 12 minus 1.2 I2 divided by 13.7. This is I1. We can do the same thing for the third equation. So this one comes down here. We'll write I3 in terms of I2, okay? So move these two to the other side equation, become 9 minus 1.2 I2, and then divided by negative 6.7, okay? So negative 6.7, or you can rewrite this as 1.2 I2 minus 9 over 6.7, okay? So this is I3, this is I1. Now both of these will go back to the first equation, okay? So then we'll have I1 as 12 minus 1.2 I2 over 13.7 equals to I2 plus I3 is 1.2 I2 minus 9 over 6.7. Okay, so this newly equation here has only just I2 as the unknowns. Then we can solve for I2. Okay, so this is a little bit algebra. Okay, if we are careful, we should be able to find the answer. Okay, so we'll do this 12 over 13.7 minus 1.2 over 13.7 times I2 equals to I2 plus 1.2 over 6.7 I2 minus R9 over 6.7. Okay, so we'll put I2 on one side. Every term has I2 on one side. Okay, so those three, and um, the rest to the other side. So maybe this guy to the right hand side or left hand side, and then this guy to the right hand side. Okay, and so then we have 12 over 13.7 plus 9 over 6.7 will be equal to the three terms with I2. This guy is 1 plus 1.2 over 6.7 plus 1.2 over 13.7 I2. Okay, and then we can find I2 by dividing both sides with this gigantic parenthesis there. Okay, we can find out I2 then equals 1.752 amps on that. Okay, and that's I2, which if we look back is the voltage through the 1.2 ohms. So then we can say that's for the I of 1.2 ohms. Okay. Then now if we look back here, now we have I2, so you can put things back here. This equation over here, so then you'll have I1, okay? So we can find I1 then. I1 then will be equal to the 12 minus 1.2 times I2, that's 1.752 amps, okay, divided by the 13.7, so then I1 is 0.7225 amps on that. And we do the same for I3, just plug in I2 in the expression of I3, so this will be 1.2 times I2 1.752 minus 9 over 6.7 is 6.7. So that will be equal to negative 1.029 amps. Okay, so we get negative here. Don't worry, it's only simply means that when we start that the current I3 is in this direction, it's actually the real direction actually is here. So I3 actually goes in like that. Okay. So at point A, actually I1 and I3 comes in. So I1 and I3 comes in and then becomes I2. Okay. That's what it all meant. So not to be worried about that. Okay. And then we can kind of look at those numbers, right? So I1 down here, and then I3, if we forget about the minus sign, so these two numbers should be adding up to be this guy, okay? And that's consistent, so that's fine, okay? So that's how we find the solution for this complicated example, okay? So apply Loop's rule and junction rule to as many equations as the unknowns you are solving for, and then solve for the unknowns, okay? So just follow the procedure similar to this guy, and you'll find it, okay? So here, first, maybe you have to do this in 2 pages, okay? And then the second page there, all right? Okay, so we'll go back to the slide. Okay, so we have done that. Lastly, we will take a look at the multimeters one by one. So you guys have used a voltmeter to measure voltages. So to measure voltages, you actually gonna to just put the actually I think we'll talk about ammeter first, okay? But we can talk about voltmeter first, okay? So voltmeter is the one used measures voltage. So to do the voltages, simply plug in the two terminals of the voltmeter to the terminals, the two terminals of the elements that you want to measure the voltage across, okay? So you can see voltmeter is parallel to the element you are measuring the voltage. So then in that case, you want the resistance of the voltmeter as large as possible. So then when the current comes in here, it splits into two. So if you have very large resistance here, current through this guy is V over R. If R is very large, then current is almost zero. Okay, so then the current still should be mostly going through the element you are measuring. Okay, so for voltmeter, you need as large a resistance as possible. Now going back to the current meter, ammeter. Okay, so ammeter is to measure current. So in that case, you want to measure the current that goes through an element. So then the ammeter will be in series with the part of the circuit you want to measure. So then this you do not want to disturb the current through the circuit. So then the resistance should be as small as possible. So an ammeter is pretty much just like a conducting wire in that case. So it has very small resistance. Okay. Um, in that case, so it's not disturbing the current going through the rest of the circuit. And because of that, the resistance here is very small. So it's you need to be very careful when you are measuring the current, because if you accidentally put this guy parallel to an element, then there's very small resistance in this guy. So the current going through this guy will be very large because I equal to V over R. So then you will burn the ammeter very quickly. There's a fuse inside it to protect the further damage of the ammeter. So you will likely very easily to burn the fuse of the ammeters, and then you need to replace it before you can use it again. Okay, so be careful about the ammeters when you are doing the current readings. All right, another meter is called the ohmmeter, which is used to measure the resistance of a part of a circuit. So for this one, it's okay. It's pretty safe to do. Okay, so you don't need to worry too much about it. Okay. Some old-fashioned ohm meters you maybe see like this is in the algorithm logarithm scale, okay, for the readings. All right, so quickly recap, we look at the complex combination of resistors. If then we actually treat one part of the circuit that is either just purely series or either purely parallel to each other, and then replace that with a resistor, equivalent resistor, and then analyze the circuit step by step from that point on. Find the next part that's purely just in series or in parallel, and then replace that part with another resistor, and then move on, so on and so forth. Okay, if you have more than one battery in the system, then you have to apply Kirchhoff's rules to solve for as many unknowns as you are looking for in the circuit. So then you'll be setting up as many equations, independent equations, okay, for that. We also look at DC voltmeter and ammeter, and then also ohmmeter briefly. But that will be it for today. Okay, I will see you guys in another time.